So one way to think about phase transitions is imagine that I take a block of ice and then I supply heat to it at a constant rate and I look at what happens to the ice. So I supply heat at a constant rate to a block of ice of fixed mass or whatever. Okay? And while doing this, I can plot a graph of what is the temperature of the ice as a function of time. So because water is very simple to use the Celsius scale, let's use the Celsius scale. Okay, so 0 is the point at which it will turn into a liquid, which is here. 100 is the point at which it will turn into a gas, somewhere here. And let's suppose that I start at a sample of ice. That means I'm below 0, somewhere around here. So as you start to add heat, the temperature of the ice starts to increase, something like this. Okay? But once it reaches 0, it suddenly stops increasing for a while, and it will stay at 0 for a certain amount of time. Then suddenly it will start to increase in temperature again until you get to 100. Then again it will stay at a constant temperature at 100 for a certain amount of time, which is longer in this case. And then eventually it will start to increase. Okay, so some things to note about this graph. Firstly, the gradients here, where the temperature is increasing, this is proportional to the heat capacity. Okay? Inversely proportional to the heat capacity. So ice has a lower heat capacity than water, so that means the gradient here is steeper, the gradient here is less. It takes more energy to heat liquid water than it does to heat solid water, or ice. But what I really want to talk about is these periods of time. When you reach 0 and when you reach 100, you're supplying heat to the system, but the temperature is not changing at all. And you should be able to guess the reason. What's happening here is that the solid water, the ice, is turning into liquid water. Okay? So at this point, all of the water is still solid, it's still ice, but at this point it's all melted. It's all turned into liquid water. And the same is true here. At this point, the water is all still a liquid, and at this point, it turns into a gas. Okay? Now, because you're supplying heat at a constant rate, that must mean that between here and here, you put a lot of energy into the system, but the temperature doesn't change. Now, that means it takes energy to change the state of the liquid from ice to liquid water, and it takes energy to change liquid water into a gas. So to write that clearly, what's going on here is that the solid water is turning into a liquid, and what's going on here is that the liquid is turning into a gas. And what you learn from this graph, is that it takes energy to change from solid to liquid, and from liquid to gas. And there's one more point I have to add. It is also possible that a solid substance can turn straight into a gas without turning into a liquid in between. Okay? So you also get a transition going from a solid immediately into a gas. Okay? This doesn't happen with water at room pressure. So if you heat water on the surface of the Earth at atmospheric pressure, it doesn't happen. But if you go down to very low pressures, about 200 times less than the pressure on the Earth, then this happens to water. So at pressures 200 times less than atmospheric pressure, ice turns straight into water vapor without the liquid stage in between. So it depends upon the pressure. Carbon dioxide, for example, does this at room pressure. If you have carbon dioxide at room pressure, it's either a solid or it's a gas. It's never a liquid. So I called the title of this section phase transitions. That's because these things, solid, liquid, gas, are known as phases. We say the phase of the water is solid, the phase of the water is liquid or gas, and the change, solid to liquid, liquid to gas, or solid to gas, are called phase transitions. So a phase transition is the change in state of a substance from solid to liquid or gas. Probably write that here. Okay, so solid, liquid, gas. These are called phases. And when you change from one phase to another, it's called a phase of transition. Okay, so I told you that one of the things we learned is that it takes energy to make a phase transition. So we can quantify how much energy do you need, and these things are known as latent heats. So I can measure the energy required. The latent heat of fusion is the energy required for this. The energy required to turn solid into a liquid is known as the latent heat of fusion, and it's given the symbol LF, F for fusion. So this is the energy needed for solid to go to liquid divided by the mass of the substance. Okay, so there are some more. The latent heat of vaporization is the one where you go from a liquid to the gas. This is energy. Liquid to gas divided by the mass of the substance. Okay, and then finally, for some substances at some pressures, you can go from solid to gas, and this is called the latent heat of sublimation. So LS for sublimation, and then this is the energy to change solid straight into a gas, again divided by the mass of the substance. Okay, so the units of all of these things, obviously it's an energy divided by a mass, so the units of all of these things are joules per kilogram. It's an energy divided by a mass, it's joules per kilogram. So I want to give you some examples of what these numbers look like. So I'm going to give you them for water at room pressure, at atmospheric pressure. Okay. So first of all, when you heat the ice, the heat capacity CV is 2.22 kilojoules per kilogram per Kelvin. So that means it takes 2,220 joules to increase the temperature of 1 kilogram of ice by 1 degree. Then you've got the latent heat when the ice melts. This is the latent heat of fusion. And for water, this is 333 kilojoules per kilogram. Which is a much bigger number than this. Okay. So then we go into the phase of liquid water. When we heat the liquid water, you find a heat capacity of 4.18 kilojoules per kilogram Kelvin. And then finally, when you turn the liquid water into a gas, you find a latent heat of vaporization of 2,260 kilojoules per kilogram. Okay, so you see from here a couple of things you can note. As I said, the heat capacity of liquid water is bigger than the heat capacity of ice, so it takes more energy to heat liquid water. And secondly, the latent heat of fusions is much bigger than the energy required to increase by 1 degree. So for water, when I drew that graph of the temperature against time, it's 0, it's 100. For water, you would find that it spends most of its time at the phase transition points. This is about 100 times bigger than that. This is about 500 times bigger than that. Right? It would spend a lot of time there, quickly increase, and then spend a long time here. Okay. So the time taken, the energy taken to change the phase, in this case, is much greater than the energy taken to go from 0 to 100 degrees. And you know this already. If you ever try and boil a kettle of water, the time it takes to boil the kettle, that's the time it takes to go from, about 20 to 100, is quite short, maybe a couple of minutes. But if you wait until all of the water in the kettle has disappeared, you have to wait a long time. So it's quite cheap to change the temperature of the water, but it takes a long time, it takes a lot of energy to change the phase. This is different for different substances. For water, it looks like that. Just before we finish, I want to just give you some terminology. So I said there were 3 phases, which are solid, liquid, and gas. And it's possible that, depending upon your temperature and pressure, to go between any of these phases in any way. So you can go this way, or that way, or you can go this way. Or, okay, let's be consistent. Go this way, or that way. And you can go this way, or that way. And each of these processes has a different name, okay? Which it may be useful to know, so I'll just give you the terminology. So, the first ones we already talked about, when a solid turns into a liquid, this is called melting. Solid turning into a liquid is called melting. A liquid turning into a solid is called freezing. Then a gas turning into a liquid is called condensing. A liquid turning into a gas is called vaporizing. But you also see the terms used, boiling and evaporating, which are different processes, but both involve the change of a liquid to a gas. And finally, a solid turning into a gas is called sublimation. and the gas turning into a solid is called deposition. So that completes the terminology there. Okay, so we're going to carry on from where we left off last time. So if you remember, we were talking about phase transitions. At the end of the last lecture. And a phase of a substance is whether it's a solid or a liquid or a gas. These are called phases. And when the phase changes, for example, when ice melts and becomes water, we call this a phase transition. Okay? So phase is solid, liquid, gas, and a phase transition is a change of phase. Okay. Now, you can see how the phase depends upon the thermodynamic properties of the system by drawing what's called a phase diagram. And this is where you simply plot a two-dimensional graph with temperature going along here, pressure going up here. Okay? And depending upon where you are on this space, the system will either be in a solid or a liquid or a gas phase. Okay? So for example, if, say, atmospheric pressure is here, then at low temperatures we know that water is a solid. At some point it will turn into a liquid, and then at some point it will turn into a gas. Okay? So we can divide this two-dimensional space into regions corresponding to the solid, liquid, and gas phases. Okay? Now, if you do this experimentally, you find a similar sort of shape for most substances. So if I just draw it schematically, it looks something like this. There's a dividing line which goes up something like this. Then there's another dividing line which goes up something like that. Okay, I think that will do. Okay. Like this. Okay. So we've split the space into three different regions roughly, and these correspond to the solid, liquid, and gas regions. If we are here on the diagram, this corresponds to high pressure and low temperature. Okay? So at high pressure and low temperature, we should expect to find a solid. Right? High pressure, low temperature, we should expect to find a solid, and that is indeed what you do find. So this region is the solid region of the graph. In the opposite case, if we're down here, this is high temperatures and low pressures. So here we would expect to find a gas. And that is indeed what you do find. And then at intermediate temperatures and pressures, you will find a liquid. Okay. So for example, if I suppose that this is a picture of water, and let's suppose atmospheric pressure is somewhere here, and I increase the temperature, then I start out with ice, that's solid water. Then this point, the water will melt and become a liquid. So here on the graph, this is 0 degrees Celsius. And as I heat up more, it reaches this point, and then it will boil and turn into a gas. So this point here would correspond to 100 degrees Celsius for the case of water. But different substances have different values, of course, for the boiling points and the melting points, but the shape is usually the same. So there are a few interesting things I want to note about this diagram. The first of all is that this line, the distinction between solid and liquid, extends forever. Okay? So I can't draw it forever, but this line goes on and on and on forever. Okay? But this line, which is the distinction between a liquid and a gas, is only of finite length. So it stops somewhere on the diagram. Okay? That means that if you go above this critical temperature here, then there is no distinction between the gas phase and the liquid phase. If you go to high enough temperatures, there is no distinction between a gas or a liquid. So I will explain a bit more about this. There's a video I'm going to show you later. Another point which is interesting is this point here. If you're at exactly the right pressure and temperature, then you can get solid, liquid, and gas all existing together. So at this point in the diagram, all three phases can exist together. Okay, so most substances show both of these points. This point here is known as the critical point. This one here. And this one down here is known as the triple point. Critical point and triple point. And I can give you the values for water. Okay. If I call this the temperature here, T3 for triple, and the pressure P3 for triple, and up here I call the pressure PC for critical, and the temperature TC for critical. Then for water we find that the triple point first, the triple point temperature is 273.16 Kelvin, and the triple point pressure is 612 pascals. That's the triple point, and the critical point, the critical temperature is 647 Kelvin, and the critical pressure is 2.21 times 10 to the 7 pascals. Okay, so if you remember that 0 degrees C corresponds to a temperature of 273.15 Kelvin, that's what I told you last time, you can see that the triple point temperature is very close to the freezing point at room temperature, at room pressures. Sorry. So the triple point is very close to the freezing point at room pressures. And in fact, in the case of water, this triple point temperature is defined. The Kelvin and the Celsius scales now are defined in terms of this value of the triple point of water, because it's experimentally possible to measure it very accurately. Okay. And you notice also for water, the critical point, the temperature is about 400 degrees Celsius, so fairly hot, but not that hot. But the pressure is very, very large. This is about 200 times atmospheric pressure. Okay. So in order to reach the critical point of water, you have to go to very, very high pressures. So we never usually see it under normal conditions. Okay. Now I mentioned something that was interesting about this critical point. I want to show you a video now. I said if you go to high enough temperatures, there's no distinction between what's a liquid and what's a gas. Okay? So that means we can imagine two scenarios. I can start off here, say, where I'm in a liquid phase, and then I can increase the temperature and go to here, where I'm in a gas phase. Right? If you do this, then you see what you usually see when you boil some water in a kettle or on a pan. Here you've got water, you heat it up, it starts to boil, the gas, the liquid, the gaseous water vapor escapes, and if you boil for long enough, then all of the liquid turns into the gas. Okay? But if you've got good enough equipment, it's also possible to go between the same state going around this way. Okay? Now, when you cross this line, that is when you see the water start to boil and turn into a gas. But if you go around this way, avoiding this line because of the critical point, you never see the liquid boil. Okay? So you start off with a liquid, you end up with a gas, but you never see any boiling in between. The two phases go continuously, smoothly from one to the other. Okay? Okay. So this region up here, beyond the critical point, is known as supercritical. Super because it's above the critical point. And I've got a video now which is showing you a process similar to this. So the way you can go from a liquid into a gas without boiling in a continuous transition. Okay, so this is going to be the video here. This is a video I found on YouTube, by the way, so you can just go to YouTube and watch it on the link here. I'll put this on Cyber Campus at the end of today. This is a video made by Stefan Passon, who's at the university in Brunswick in Germany. And it's showing this supercritical fluid. So it's showing what substances look like when you go above this critical temperature. Okay. Now, let me explain something about it. Firstly, it's not water. Okay. So you see inside here you've got a little glass cell. And this glass cell is held at very high pressures. So you get these very strong bolts here. This is a metal here. And inside you've got glass. Okay? So it's held together at very high pressures, and inside of here is actually carbon dioxide in this video. Okay? It's carbon dioxide because for water you have to go to incredibly high pressures to see the critical point. But for carbon dioxide it's not quite as high. It's only about 70 times atmospheric pressure, so it's easier to do. Anyway. So you've got carbon dioxide inside here, held together at very high pressures. And you can see, this is a still, behind there's a thermometer, which is measuring the temperature in the cell. Okay? So the temperature there is, on this picture, is 33.1. The critical point is around 31 degrees C for the case of carbon dioxide. So as you watch the video, this is the temperature you need to look out for. This is when you will see the change in behavior. Okay. Okay, so hopefully I can show you the video now. Okay, no, before I show you a video, let me explain you a bit how it works. I need to use this diagram again. You don't need to copy this again, but I'm just going to clean it up for my purposes now. Okay. This is a liquid and this is a gas. Okay. So what you've got here is you've got a cell which is filled with carbon dioxide. Okay? Now, suppose that I had the whole cell and the whole of the carbon dioxide was only in a liquid state. Okay? And then there's nothing else in the cell. Now, in this case, the pressure here is 0. Okay? Right? Because this is empty. Apart from the carbon dioxide, it's empty. So the pressure is 0. But if the pressure goes to 0, then the carbon dioxide will try to turn into a gas. Okay? So what happens is, if you fill this cell with the correct amount of carbon dioxide, then you get an equilibrium state where you've got liquid carbon dioxide as well as gas carbon dioxide, okay, in an equilibrium. So the liquid and the gas quantities arrange themselves exactly so that you fall on this line. If there was more liquid, that would decrease the pressure and create more gas and push you back to the line. Okay. So what happens is, as you heat the carbon dioxide, okay, so if I heat the carbon dioxide, I will try and move it this way. That's heating. Temperature is increasing. But if I do this, then more of the carbon dioxide will try to turn into a gas. Okay? As the carbon dioxide turns into a gas, that increases the pressure and pushes it back up this way. So you heat it, more carbon dioxide turns into a gas, and that increases the pressure to this point. So what you find is, as you heat this system, you always stay along this line. Okay? Because changes in temperature, the pressure is exactly balanced by converting more or less of the carbon dioxide into a gas. Okay. So as you heat it, you move along this line, and if you go far enough, then you will hit this point and then keep going. And at this point, you will see the supercritical behavior. Okay. Right. So that's what we're going to see. What's it about there? Okay, so you've got this cell that I told you about, and you can see there's a dividing line. So in the bottom of the cell, you've got liquid carbon dioxide, and above the cell, you've got gaseous carbon dioxide. Okay? And this is the dividing line between the two. Now, I only want to show you part of this video. If I go to about 2 minutes. This, okay. Okay, so the line he's marked on, this is a drawn line. Okay, it's not a real line. This is the level of the liquid carbon dioxide initially in the cell. Now, if we play it, you see that the temperature is increasing. As the temperature increases, the level of the liquid is rising. That's the level of the liquid here. Okay, and that's what I wanted to show you. So you see that by this point, as we increase the temperature, the line which divides the solid and the liquid has just disappeared, right? So I'll show you again. Okay. So keep your eyes on this line which divides the solid, divides the liquid and the gas. This line here. And you can see it becomes turbulent, and then at some point the line just disappears. Okay? Yeah, you can see that happening, right? So what you're seeing, I'll just put it on once more. Okay. What you're seeing is that at low temperatures you can divide the liquid and the gas into separate phases, but at high temperatures, once you go above this critical point, they become the same phase. So at low temperatures, liquid and gas are different phases, but above the critical point, you get a single phase here, which is called the supercritical fluid. Okay. Okay, so that's all I wanted to show you. And now the video, they do the reverse. So now they reduce the temperature from above supercritical, and they're reducing the temperature. Okay, and you get this condensation. And again, you see as you reduce the temperature, the system again divides itself into two halves. So you've got liquid on the bottom and gas on the top. Okay? And then he goes, it's okay. I'll just show you that one more time. Okay, so as you reduce the temperature, you get this condensation effect, and then the two phases divide again. Okay, so there's lots more to this video. They do it under various initial conditions, so you can look at this in your own time. But what I wanted to show you is just the nature of this point here. So if you're at low temperatures, there is a distinction between the liquid and gas phase. But as you increase the temperature in the cell, above some critical point, the two phases become the same. Okay? And you can go continuously from a liquid to a gas.